ChatGPT, autonomous driving, DALL-E, personalized shopping and spam filters. What do all these share in common? Unless you have been living in the rock lately, you probably guessed right. These are part of a recent wave of artificial intelligence systems.
Artificial
intelligence
is making rapid strides.
But have you ever wondered how these AI systems work? The fact is, there is one underlying algorithm which is used across all these AI projects you hear about. That algorithm is tasked with teaching these AI models how to learn from data. What is an AI model, you ask? Well, let's rewind a bit and talk AI history. In a paper published in 1936, Alan Turing, the father of what is now computer science, articulated a mechanism to simulate the process of computation which humans used to do. He effectively invented the underlying concept of a computer. Computers were meant to be machines that would simulate thought, but ended up simulating the step-by-step calculations used to execute a procedure, what we now call algorithms. Then comes John von Neumann, the father of the computer architecture. His first thought was that it might be possible to replicate intelligence by merely automating reason using a computer which follows a set of procedures to execute a set of hard-coded tasks. This led to what came to be known as the classical AI approach, which led a revolution in what came to be known as the automation of labor, now used in factories and mass manufacturing processes. However, this wasn't enough to simulate intelligence, as some intelligent tasks couldn't be hard-coded, because we ourselves don't know how we execute them. An example would be how we recognize human faces. So then came a new wave of researchers who took inspiration from the human brain, learning how the brain works and trying to mimic it. They led a new AI revolution using an approach different from the classical AI approach. Pioneers who led this revolution were Herbert Simon and Alan Newell, both of whom paved the way to the establishment of new mechanisms made to teach machines to learn from data how to do tasks based on reward and punishment signals, instead of hard-coding these tasks. Now, the idea behind reward and punishment stemmed from some basic understanding in neuroscience, which deals with higher-order learning processes in the brain. Mammalian brains are observed to use positive and negative signals to reinforce certain behavior and inhibit others, respectively. This is usually expressed in the form of dopaminergic activities like dopamine release for receiving a fulfilling reward, or a dopamine inhibition for receiving a disappointing punishment, respectively. An algorithm referred to as backpropagation with gradient descent optimization was developed to mimic the positive/negative rewarding system in what is known as error-driven learning through iterative cost minimization. Now, it's not your job to understand the fancy math behind the higher-order regression with its multi-dimensional calculus used in this algorithm. This job is for researchers like me. Instead, what you need to take from this is that this algorithm merely does some higher-order statistical calculations to minimize the number of times an AI model does something wrong. Be it a wrong classification of a picture, a wrong prediction of the correct words in a sentence, a wrong generation of musical notes or beats, a wrong drawing of a generated image, and so on and so forth. This is possible by first providing a large amount of data that was pre-labeled correctly, second, running each data sample through the network iteratively, and last, sending a negative punishment signal every time the network guesses incorrectly. Now, of course, this is a grotesque simplification, and the devil always lies in the details. But overall, this algorithm formed the underlying basis for the development of neural networks, which progressed into multiple deep layered variants. These paved the way to a new approach for AI that evolved to establish a new field dedicated to only the engineering of these deep neural network architectures, which is now known as deep learning. In deep learning, we see the realization of sophisticated artificial neural network architectures like CNNs, RNNs, LSTMs, and finally the elephant in the room introduced by Google in 2017, the transformer. Recent innovations in the field of AI were built upon the introduction of these artificial neural networks. They are the crown jewel of the field of artificial intelligence. To give an analogy, an artificial neural network architecture is like an engine which can be used to power a variety of car models. ChatGPT is powered by the transformer architecture. DALL-E is also powered by the same transformer architecture. Self-driving cars are powered by convolutional neural networks, CNNs, another type of neural network architectures, and so on and so forth for a large variety of AI projects. You see, a handful number of these architectures power the vast majority of all AI projects across a wide spectrum of domains. In the recent decade, these artificial neural network architectures became the foundation of many profound technological utilities, which are provided by data scientists across a vast array of industries. Technologies that require image, sound, or speech classification in what is known as recognition task AI, as well as technologies that require image, sound, and speech generation in what is known as generative AI. All are prime examples of technologies which the introduction of artificial neural networks has had a great impact on, as they boost the performance of these tasks and allow for the realization of other tasks which were never possible before. In 2024, almost every technology company, inside and outside the bounds of Silicon Valley, uses some form of an artificial neural network architecture in one way or another to solve problems and achieve intelligent tasks integrated to their business model. All in all, these architectures pave the way for the next wave of automation. This time not labor, but instead mental automation. Yet every rose has its thorns. Artificial neural networks come in a variety of different configurations. We got ANN, CNN, RNN, LSTM, GAN, autoencoders, transformers, vision transformers, and many more. But the ones that proved most successful were CNNs for image classification and computer vision tasks, LSTMs for sequence classification and language processing tasks, but most importantly, a more capable architecture introduced by Google in 2017, commonly known as the transformer architecture. This powerful neural network architecture succeeded its predecessors in natural language processing and paved the way for the recent boom in generative AI. All large language models, which you heard about recently, including ChatGPT, are based on this architecture. Not only that, but in fact all the wonderful AI projects which boomed in 2022 after the introduction of ChatGPT are built on top of the same engine, the transformer. If you recall, artificial neural network architectures are like engines which power various car models. If ChatGPT, DALL-E, and Gemini represent different car models offered on the market, then transformers and CNNs are like the most powerful two engines in this market. However, there is one thing these different neural network architectures all share. That is the way they are built to learn. You see, all these architecture designs gone through many modifications and variations over years which varied them from one another and made them successful in different AI domains, except for one thing which never changed and which their design was tailored around, which is that one and only one learning algorithm which these models use to learn from data. That is backpropagation with gradient descent optimization. Yes, that mouthful name I mentioned earlier. Over the years, however, AI researchers noticed how the optimization-based neural networks have a few detrimental problems. Mainly the high demands of processor computations required to learn simple tasks measured in flops, as well as the extremely high demand for power/energy consumption relative to the human brain. What is a processor computation, you ask? Well, let's drift a little into the world of the semiconductor industry. Your laptops, PC, smartphones, smartwatches, smart TVs all share one thing in common: processors. A processor is a hardware chip which is designed for the single task of executing large volumes of instructions. An instruction is like a small calculation task, for example adding two numbers or multiplying two numbers. Now, instructions can be more complex, like comparing numbers or skipping/repeating other instructions, etc. Processors come in two main types, mainly sequential executors of instructions, called CPUs, or parallel executors of instructions, called GPUs. They formal deal with executing instructions in a sequence chain, one instruction after the other, while the latter deals with executing multiple instructions simultaneously in parallel. These processors typically perform billions of these instructions in 1 second. So for example, a 5 GHz processor can theoretically perform 5 billion additions in 1 second. The hardware units which perform these calculations are referred to as processor cores. CPUs and GPUs mainly differ in the number of these cores which are fit to work together. CPUs come in 4 to 16 cores, while GPUs can go as far as 10,000s of cores. Now to head back to our main point, GPUs are what AI models use to perform the mouthful learning algorithm we mentioned earlier. To put it in another way, over time, GPU companies like Nvidia started to tailor their GPU designs to fit the learning algorithms of these AI models by providing specialized processor units called tensor cores, which perform the exact computations required for the AI models to learn from the data. Mainly huge volume of matrix multiplication instructions. On another plane of existence, the world of analog device designs, researchers were trying to solve a problem found in all such processing units, that is the von Neumann bottleneck problem as it is known. To put it simply, these processing units are designed to perform billions of calculations, aka instructions, but are limited with how they store and retrieve these instructions to and from memory. To give a simple analogy, imagine a math exam hall with 100 students. Each student is tasked with solving 10 math problems and choosing the correct answers in the exam paper. The catch, however, that every student is only allowed to solve one of the 10 exam problems at a time. Once they have solved one of the 10 problems, they are required to submit their papers to a central hub. And once they have submitted their paper, they are required to retrieve that same exam paper sheet they just submitted to solve the next problem in the exam sheet. They continue to go back and forth until they have answered all 10 problems. In other words, a total of 10 submissions and 10 retrievals of that same sheet of paper for each and every student. And the second catch? When doing these trips, all 100 students are required to pass from the exam hall onto the central hub through one narrow door. Sounds dumb and inefficient, right? Well, unfortunately, that's how modern CPUs and GPUs, which are found on the device you're watching this from, run. That's of course if you substitute math problems with processor instructions and the central hub with centralized memory architectures. Now I can hear your thoughts. There's definitely room for improvement. A more efficient way exists. First, why do the students have to go back and forth and waste all that time doing 10 trips when they could just answer all 10 problems at once and then submit the paper? Second of all, why do they all have to go through the same narrow door to pass from the exam hall onto the central hub? Why not build more doors? Well, they do build doors, known as wide memory buses, but it's just impossible to build as much doors as there are students, or at least that is if we use traditional hardware devices. You see, that's what our analog device research guys figured out. The memristor. The memristor is a device that acts as both a memory storage and a resistor. Now, you don't need to worry about the electronics aspect of it all. All you need to understand is that this great device is capable of bypassing the need for that central hub, the centralized memory architecture. Instead, allows for what is known as finely grained distributed memory architectures. This act of saving all these round trips and creating as many doors as there are students using this memristor device doesn't only save huge amount of wasted time, especially when you multiply our example on the order of thousands of students solving billion math problems per second, they also save so much energy in the order of 100 times less power. You see, the brain has 100 billions of neurons and quintillion connections between these neurons, which processes quintillion instructions at a time. That's 1,000 trillion. Yet it only consumes a light bulb worth of electricity power in terms of wattage. This ties us back to the AI models we were talking about. The AI architectures suffer from a very terrible limitation. That is, they all use a learning algorithm, the mouthful named one if you remember, which is extremely inefficient in terms of how many calculations are required and in terms of the way the traditional hardware GPUs use execute these instructions. Therefore, the problem lies in this inefficient learning algorithm, which consumes a lot of energy, requires a lot of data to learn, and take long times to train. All these problems make the learning algorithm bad at real-time application, or what is arguably worse is that the algorithm is inherently too complicated to be fit in those low-energy, low-power memristor-based hardware core processors. So not only the algorithms make these architectures, the engines, inherently slow, but also they are too complicated to run on any future hardware cores with distributed memory architectures. It's like driving a Mustang with a Ford Model T engine on a sand beach. You have the potential for speed and power, but the inefficient engine can't handle the conditions, leaving you stuck and underperforming. Therefore, that one learning algorithm which the entire AI industry is based on provides an enormous pain point to the future development of this industry.